All right. Thank you. Okay. So, routing lecture 3. Starting off today in computing, it's Mike Makula's birthday. We mentioned last time, the second semiconductor was invented by Bob Noyce, who went on to found Fairchild and Intel. Mike Makula worked for both of those also. He also was Apple employee number 3. He was like an angel investor for Apple. He also, at different points in time, served as the CEO and the chairman. He wrote some software for them, despite being sort of a management type in the early days. I think he was also a key player, if I remember this story right, in both the ousting of Jobs and the rehiring of Jobs. So Steve Wozniak said that, while he and Steve Jobs get a lot of credit, Mike Makula was probably more responsible for the early success. So a kind of impressive guy. All right, so today, I'm going to start out by taking a look at some of the self-test questions. Going to have an introduction to Project 1, sort of. Going to finish talking about distance vector protocols. Then we're going to talk about link state routing protocols. Then we're going to switch gears a little bit and talk about learning switches and a spanning tree protocol. And then, if we have time, we will play the spanning tree game. All right, so starting out with some self-test questions. So here is one. Routing ensures reliable delivery of packets between end hosts. And so most people got the right answer, which was false, but there was a fair percentage of people who were confused and thought the answer was true. I thought this was really interesting. Maybe somebody will clue me in, but an earlier question on this same self-test was, if you have valid routing state, does that mean the network will never drop any packets? And 90% of people said no. So if packets can still get dropped when you have bad routing state, then the network can't be ensuring that they're reliably delivered, right? This seems to be a conflict to me. So routing may be necessary for reliable delivery, but it's not sufficient, right? We're still talking about best effort networks. So moving on, we had this question, does the no loops, no dead ends theorem only hold true for destination-based forwarding? And most people got the right answer, no, but like a third got yes. And so I said, this is copy-pasted straight out of lecture 5. Same basic no loops or dead ends condition generalizes to at least any other system that does deterministic forwarding based on fixed packet headers. That is, it's not limited to destination-based routing. So it's not. We will probably come back to that a little bit next lecture. All right, this one. Routing occurs when a data packet arrives at a router and is sent out another port. And so this one, again, most people got the answer. This was false, but it was pretty darn close. So when a packet arrives, a router forwards it to one of its neighbors. This is copy-pasted from previous lecture there. So when a packet arrives, a data packet, the router forwards it to one of its neighbors. So that's the act of forwarding, which is being described here. If you change that first word from routing to forwarding, then the statement is absolutely true. Forwarding occurs when a data packet arrives at a router and is sent out another port. Yeah?
For the first question, is routing guarantees the delivery. Is that also should be forwarding?
No. So let's see here. The question was, routing ensures reliable delivery of packets. Yeah, I don't know what to say about that. Holy cow. that was not an improvement. All right. This is the state of the world. Not reliable. Forwarding doesn't ensure reliable delivery of packets between end hosts either, right? Like, nothing we've talked about so far actually guarantees that packets are going to get delivered, right? They could be dropped at any time. Forwarding is trying to deliver them. Routing is working to try to help forwarding help deliver them. But, essentially, we've talked about like queues, for example, right? And when the queues fill up, we'll drop packets. And so that can happen. And so we're not going to talk about like basically mechanisms to sort of fake reliability until a couple weeks from now. Okay, so this statement. Forwarding occurs when a data packet arrives at a router and is sent out another port. That's what forwarding is, right? Forwarding was like with the envelopes. It's when you actually hand it to someone else. So routing is what determines which neighbor to forward to. Yeah. So any questions on self-test questions? All right. So Project 1 was supposed to be released today. I have just been told that the plan is now to delay it, I think, for a week. The reason is, well, you still got to do it. The reason is the decision was made that this will be the last time that we do it in Python 2.7, and we will port it to Python 3 between now and the next time it's offered. And then yesterday, Homebrew yanked Python 2.7 out of Homebrew. So Mac users now may have a problem getting it to run. So as it happens, last Friday, I ported part of it to Python 3, so we're going to now test and actually make sure that it'll work on Python 3 and release it in a little while. So. All right, so Project 1, a little bit delayed. All right, so finishing up talking about our favorite routing protocol, distance vector. So last time we started building up from like our simple sort of distributed Bellman-Ford into like an actual routing protocol, right? And so like we refined our update rule. We said that we should always trust our neighbor. If we're using that neighbor as our next hop for a route and it tells us a different advertisement, we should always include that even if the cost is worse, right? We resolved some wacky problems using split horizon. Without that, we saw like a case, for example, where we could end up with routes that go backwards. We ensured that we eventually converged instead of counting to infinity by sort of adding this like artificial limit to infinity, right? So eventually we stopped counting. We made it robust to packet drops and reordering by, re-advertising our routes periodically. We saw that it can adapt to new links easily, right? Basically, when a new link comes up, you send advertisements out of it, and it basically just works. And we saw that we can identify failed links and adapt to them by essentially, when we miss advertisements, we can let our current routes time out, right? And that's our way of sort of detecting. And we can then remove those timed out routes. And so that's basically where we finished off last time. So I want to really quickly revisit that last one where we were using timeouts to handle failed links. And I'm going to go through this example. I'm going to do no triggered updates. I'm not going to show every update. But remember we got to this point here at time 10 where R1 is sending periodic updates every 10 seconds, and it sends this one, which charges the one on R2 back up to the maximum time to live of 21 seconds. And then right after that happened, the R1, R2 link failed. The projector failed. And so R2 doesn't know that this route is no good yet, so it eventually, at time 15, advertises it to R3, recharging R3's entry. 5 seconds after that, R1 sends its updates again. The one to R2 never gets there because the link is down, so the TTL on R2 decreases. The one on R3 gets ignored because it's worse than the current route. 5 seconds later, R2 recharges the route on R3 again. The TTL on R2 is continuing to decrease, right, because nothing's charging it up. 5 seconds later, R1 sends its routes again. This is the same as last time. R2 doesn't get it, R3 ignores it. But R2's route is now almost dead, right? It's just about to time out. So 1 second later, that route expires. And so we remove it, is what we did last time. And since R2 stops advertising it, then 15 seconds later, at time 46, it's going to expire on R3 as well. So now both of these tables are empty until R1's timer goes off at time 50. R3 gets the route and accepts it, fills in that entry, which eventually gets advertised to R2, which accepts it because it's empty. And now we've converged, right? So that's how we converged last time with timeouts. So any questions on that, on how that mechanism worked? All right, so you learned a little bit about poisoning in section yesterday. So let's take a closer look at that same example that we just went through, but with poisoning. So at time 31, this route times out, right? And we removed it. And then we wait 15 more seconds for it to expire on R3, and this was preventing both R2 and R3 from having working paths, right? Like, until R1's timer goes off, like the next time R1's timer goes off at T40 actually, like there's still this expiring route in R3, right? It's still got 6 seconds left. So we don't actually get the new route until time 50. So that's 19 seconds after the route expired on R2. So there's something that we can do to improve things here. And in fact, you know, someone jumped ahead last time when I put this question out to the audience. Somebody leaped ahead and got it. And so going back to time 31 here, when the route on R2 expires, we can do something instead of deleting it. And so at this point, maybe some of you know, what can we do besides deleting it? So instead of deleting it, we create a route with an impossibly large distance. We call this a poison route. So this one with impossibly large distance gets advertised at T35 when R2 sends its advertisements. And so R3 is going to accept it, right? Because R2 is the next hop for the current route, so it's just going to blindly accept that. And it's going to say, okay, my cost is now infinity to A. So now when T40 comes around, and R1 advertises its routes, it's clearly better than the infinite costing one that it's got, right? And so this gets propagated to R2 the next time R3's timer goes off. And so that, you know, the key idea here was basically, instead of just not advertising a route, you actively advertise that you don't have a route, right? You advertise that your distance to that destination is infinity. And so we do this with this like infinitely high poison route. So this route propagates just like other routes, poisoning this entry, you know, on other routers that were using it. And so this can be much faster than waiting for timeouts, right? You only have to wait for it to be advertised. And this doesn't just work for timed advertisements either, right? Like if you get a poison advertisement and it changes your table, then that's going to trigger you to send an update, right? Because your table changed, so your neighbor's tables might change. And so this means that you can propagate dead routes basically as fast as they can reach and be processed by the neighbor instead of waiting for a timeout. So that could be much, much faster than waiting for timeouts. Does that make sense how that mechanism works, how we go from waiting for timeouts to poisoning a route? Yeah.
How does a router know?
How does a router know that a link is dead? Well, so like in this case, right? The router didn't actually know how that the link was dead, right? I mean, it didn't really know. What it knows is that this route timed out, right? Because if the link was alive, then it should keep getting charged up by every periodic advertisement. But it wasn't getting those, so it decides, it must be dead. There are other ways that it can know directly, and I'll come back to that in a minute. So, any other questions on this? Yeah.
Wait, just to clarify what you just said. When something that's maybe I'll take a route, and you mean like when the TTL itself goes down, like when it like entirely the TTL runs out and then goes to 0, or
Right. So the basic question is, do we wait for the TTL to run all the way down to 0, or does it just need to be some other number? And the answer is that you wait for the TTL to run all the way down to 0. And so basically you set the TTL usually to like some multiple of the advertisement interval, right? So if the advertisement interval is like, oh, I'm going to periodically advertise every 10 seconds, right? Then if your TTL was like 5 seconds, then you would constantly be timing it out, right? Like you would never get it charged up, basically, right? If you set it to like 11 seconds, then that's probably mostly going to work. But if it misses one advertisement, you're going to be like, oh, this route's dead. But it may have just been one unlucky packet, right? So you usually set it to some multiple, like RIP's default sets it to like 3 times the advertisement interval. So you can actually miss like several updates in a row before you're like, I'm just not getting them anymore. Does that make sense? Like why you set that, the timeout to be like some multiple of the advertisement? It gives you like multiple chances to charge it up. Any other questions on timeouts and on poisoning? All right, so besides expired route, where else did we not advertise something? Where we had something to advertise, but we didn't. Yeah?
Like, you advertise it after, like, a certain time frame, right?
For, like, a new link? Yeah, so that's an interesting one. Not what I'm thinking of. So maybe when you have a new link, maybe you don't advertise immediately. Yeah, we'll actually come back to that, but not what I was thinking of. Yeah?
Next hop.
Next hop. Do you remember what that rule is called? Split horizon. Yeah. So split horizon is this other one, right? Like in split horizon, we had a route, but we didn't advertise it to one of our neighbors. Specifically, we didn't advertise it back to the neighbor that advertised it to us, right? Why would we? They already know about this route, and we couldn't possibly be on the shortest path. So the split horizon rule is the other one. But so instead of just not advertising back to the router that gave us the route, we can advertise an infinite cost to that one. And we call that poison reverse. So it's the same exact idea as split horizon, but it's more aggressive, right? Let's walk through a really quick example here. So assume we're converged, and then R1 goes down. Sometime later, R2 and R3, let's say they advertise their routes to each other at exactly the same time. And note that these routes are through R1, which is dead, and they're about to expire. Look at the TTLs. They're like almost dead. So while they're in transit, like halfway between R2 and R3, these routes time out. Contrived example, but just making the point. So when they end up getting to the destinations here, right, they both get accepted because the tables were empty. So this is describing a loop here, right? That's what we've got now. R2 says it wants to forward to R3. R3 says it wants to forward to A. And so with split horizon, neither of these would now be advertising to each other, right? So after the TTL runs down in 21 seconds, both of these routes would expire. Does that make sense? That's what split horizon does? Yeah. So in this case, at this time, their routes are through R1. So they wouldn't advertise these to R1, because that's the upstream one, right? Like split horizon says, don't advertise it to the next hop, and the next hop at this time is R1. Does that make sense? So that's why, they're not going to advertise them to R1. But when they arrive, their next hops are through each other. And so anyway, like I said, they're going to get affected. Split horizon wouldn't advertise to each other. They're going to time out in 21 seconds. But with poison reverse, instead of just not advertising them to each other, what do we do? We advertise infinity, right? So they say, all right, R2 is like, okay, so R3 wants to go through me, so I'm going to tell it infinity. And R3 is like, R2 wants to go through me, so I'm going to tell it infinity. And so these get delivered. They get accepted due to the special case, right? Like always accept from the next hop. And so this basically now sets these routes so that they're, infinitely bad. And so, we'll never forward using a route. If you notice that the route says that the distance is infinite, you don't use that for forwarding. And so instead of having to wait for a timeout for these to go away, right? We only had to wait for an advertisement, which is either, on average, half of the advertisement interval, or it's immediate if you're using triggered updates, right? So like as soon as they got them, they would send back the poison reverse routes, and this would get resolved. Does that make sense? How this makes things happen faster? It's the difference between saying nothing and saying no, right? Yeah? So can I explain in that example split horizon?
Yeah, whether it will just keep counting it or
Yeah, so in this case, where were we? So they're here, they time out, they get delivered, we get these routes, right? And so the question is, are they going to keep counting in this case or not? And so essentially, if you have split horizon, that says don't advertise the backward cost. So there's nothing to make them count. The TTL is going to just count down to 0, right? If you had split horizon turned off and they actually advertised, then, like R2 in this case would advertise a cost of 3. R3 would accept it with a cost of 4, adding the 1, right? Which would then advertise for a cost of 5. And so with split horizon off, they would count up. But with split horizon on, you have to wait for them to time out. And with poison reverse, you don't have to count or wait for them to time out. Does that make sense? Yeah?
So what exactly is triggering the routers to send the infinite length in this case?
So the question is, what is causing the routers to send the infinite length? And the answer is basically when they get this route. So it's, where is it here? So this is when that route occurs, right? And so R2 now has this one. Its table just changed, right? It went from empty to this. So you could say a triggered update now says, okay, my table is now changed. I should send updates. And the update to your upstream one, to your next hop, is going to be infinite, right? Because that's what the poison reverse rule tells you to do. Does that make sense? If you had split horizon, then you wouldn't tell your next hop anything. With poison reverse, you'll tell your next hop infinity. Making sense? Kinda? Not really? Yeah.
So, in this example here, you're saying that like after 10 seconds, like or at like TTL 11, like you're saying that like okay, they advertise the infinity. Why would the routers accept the infinity? If our assumption is that as soon as you get any packet, like even before things went down, if our assumption is that you're setting infinity to your next hop, then normally that router's not going to accept it because it's greater than whatever it has.
Right. So like in this case right here, we're seeing it like at R2, it's getting an advertisement from R3 with a path of infinity, right?
Right.
And so you're saying, why would it accept that?
Well, I guess, okay, so, yeah. So it would just because that's the next hop.
Exactly. This is that special case that we said, where if you get an advertisement from the route that you're currently using as your next hop, always accept it, even if it's greater. Yeah?
I think what we're asking is that, so binary reverse is to not to wait till TTL expires, but to know you have to, its infinity, you have to wait till TTL expires.
To know its infinity, do you need to wait for the TTL?
Like, is there an special event that tells you that it goes down?
Yeah, so in poisoning, right, and this is the difference between poisoning and poison reverse, right? Like when a route expires because the TTL runs down, right, you can change that route to say, okay, this route is now infinite length. Instead of removing it, right, then you say, oh, it's infinitely distant, right? So that's just poisoning. Poison reverse is slightly different, right? You're still using this infinite length route, but you're doing it where you would have sent nothing because of split horizon before. And so in any case, whenever you do an advertisement, with split horizon, you never advertise a route to the router that gave you that route, right? Why would you? It's the one that gave it to you. It doesn't need it. So that's what split horizon tells you to do. Poison reverse tells you, tell the one that gave it to you infinity, that you can't reach that destination through me. Does that kind of make sense? You got lots of time to figure this out also in the project. Yes?
Can you explain how it works if R1 never goes on? Like, in the normal nothing goes on fire case,
Yeah.
what happens if they still advertise infinity?
So if nothing goes down, there wouldn't be any reason for them to advertise infinity to each other, right?
Okay, so you're saying that they only advertise infinity when they realize that the TTL is gone down. Or like the TTL.
Well, so that's the normal poisoning case. But the other case is poison reverse tells you if nothing went down, then both R2 and R3, what's their next hop? R1. And so they advertise infinity to their next hop. So both of them would be advertising infinity to R1. Does that make sense? Always to the next hop, you advertise infinity if you have poison reverse on. That prevents your next hop from trying to forward backwards through you, right? Because you're telling it, if you try to send it back through me, it's infinitely far away, right? That's what convinces it not to try to do that.
But for R2 and R3, they accept the infinity when it's sending to each other. But in the case of R1, if it doesn't accept the infinity, then R2 and R3 advertise infinity. How does R1 know?
Not to accept it. So the question is, when in the example that I walked through earlier, like as shown on the screen right now, when R2 and R3 get these infinities from each other, they know to accept it. On the other hand, I was just saying, if nothing ever went down, then R2 and R3 are both advertising infinity to R1, and R1 isn't accepting it. So why doesn't R1 accept it? Why does R1 know that it shouldn't accept it? Anybody want to? Yeah. Yeah, so in that case, with this rule that's up here, right, the next hop for that one is A, right? That's the next hop for the rule that's up there. And so it's going to do the normal comparison and say, well, I have one route with a cost of 1, and you're offering me one with a cost of infinity. So under all things being equal, I'm going to take the 1. Right? The only reason why it would take the infinity is with the special case, right? If its next hop was R2, then it would accept one from R2. If its next hop was R3, it would have accepted one from R3. All right. Yeah?
So how does poison reverse relate to what R1 is broken?
How does poison reverse relate to R1 being broken? Yeah, and so the reason that R1 is broken in this case is because that's what we needed in order to make this happen, where R2 and R3 are advertising to each other. If this route, the one that's listed in R2 and R3 through R1, if that's there, then they're not going to accept that route, right? They're just going to ignore it. So we don't get this loop in the first place. It's only because R1 was down that R2 and R3's routes expired, which is the only reason that it accepted these advertisements from each other, which is how we got the loop. Does that make sense? So that's just part of the example. That's like how this example works. Does that make sense? Yeah.
Why would you use split horizon over poison reverse?
Why would you use split horizon over poison reverse? Yeah, in general, it doesn't seem like as good of a mechanism, right? I would agree with that. People have made arguments that like, oh, well, you know, poisoning like creates more traffic, right? You have to actually go to the, you know, spend the bytes to send it. And so some people say under certain circumstances it's not worth spending the bytes. I think that's probably a weak argument, but I think that's why people would say. I'd also say split horizon, you know, some of this is historical. Like I said, you know, for all that you all came up with this split horizon rule, basically, you know, like unprompted when we were doing the activity, it did take networking researchers like 5 years to figure that out on the ARPANET. So by the way, you know, nice job, all of you. Like, round of applause for all of you. Then they came up with split horizon. And then after that, somebody came up with poison reverse. So part of it is just sort of, this was the historical trajectory. All right, so I'm gonna move on off this subject. We can talk about it in office hours if y'all want to talk about poisoning more. But so to finish up really quick, poisoning and poison reverse, in both cases, without poisoning, you would have not sent a route. And instead, we explicitly send a terrible route such that any other route would be better. And we never forward when our route is one of these terrible infinite routes. All right, so one last thing on distance vector. More events to trigger on. We know that if your table changes, that should trigger you to send updates to your neighbors, right? Because it might change their tables too. But there are other events that are useful, and so a couple of these have sort of come up in discussion already today. And so sometimes you can detect when a link becomes available. Sometimes you can detect it very quickly. And so when that happens, you should immediately send advertisements to that neighbor, right? You don't need to wait for a timer to go off to send. You can say, as soon as you know that there might be a neighbor, give it your routes, and maybe it'll use them. Similarly, sometimes you can detect when a link fails really quickly, and this is one of the questions we got. Like, how do you know that that happens? Like, usually it's because of something that happens at a lower layer. Like, at the physical layer, there might be like an electrical failure, right? Like an actual circuit breaks and the voltage goes away. And at that point, you know, okay, this link is dead, right? And so you may know very quickly that a link has failed. And when that happens, you should basically just poison all the routes that are using that link, right? Because they're not going to work anymore if the link's broken. So you can quickly poison them and then update your neighbors based on that. Does that make sense? Those things, those like a couple other events that you can react to? All right, so summing this up, back to our list of things we've been doing to convert our simple Bellman-Ford into like an actual useful routing protocol. We now can converge faster by explicitly signaling the absence of a route by advertising a poison, right, an infinite distance route. We can adapt more quickly by advertising when triggered by events, like when our table changes, or when a link goes up, or when a link goes down, if we know that for sure, right, if we've been notified by some lower layer that a link has come up or failed. And this is now a pretty good routing protocol. And so this is distant vector. This is more or less RIP. A lot of people would say it's not the best routing protocol, but it's not terrible. Any final questions on distance vector? Yeah?
I guess in the routing literature, is there any formal way of like measuring how, or defining how good a protocol is in terms of time complexity or something like that?
Yeah, so in the literature, is there any like formal way of like quantifying how good a routing protocol is? And there are a couple things that you can do. Like you can sort of look at like the order of how many messages need to be sent, and how it relates to like the network diameter and stuff like that. So yeah, you can analyze a little bit, and I may next lecture talk a little bit about that. Maybe not. We'll see where we are on time. But so to some degree. Though in general it's very context sensitive, right? It's probably going to depend on the particulars of your network. If your network's very stable, then maybe a lot of stuff is overhead, right? If your network is very dense, it may react differently than if it's very sparse, etc. So it's often kind of context dependent. Yeah. Yes. So the question is, we've been kind of looking at these small examples, and like at scale of the internet, does this go up? Do we actually have, does your little Wi-Fi router at home have like a full routing information for every host on the internet? And so I'd say, first of all, remember, we've been kind of focusing on IGPs, on interior routing protocols, right? So that's, one thing to keep in mind. And so there's also, one thing you could think about is we talked about the default route, right, in a lot of cases, which is basically like the wild card. If I don't have another routing entry to follow, use this one, right? And so, for example, your home router very much can just be default, right? Unless it's an address in your house, then it's that way out towards the internet, right? So you only need one routing entry for all that. You don't actually need to know a lot about the routing on the internet. You just need to know, the only thing you need to know is that it's not here, it's somewhere else, right? And so we'll talk about this a little bit more next time when we start to talk about addressing. So, the two things I'm trying to get at here are, one, the way that you route inside your network. You're very concerned about, like individual things inside your network, but the rest of the things you often aren't so concerned about the details of, right? So that's one of them. And the other one is we'll actually see how you don't necessarily need to know about every host because of the way addressing works. We'll see that next lecture. Yeah, good question. Anything else, or we'll move on? All right, moving on to link state routing. So this is the other class of routing protocol that we're going to look at in depth this week. And so it's newer than distance vector. It's really common as an interior gateway protocol. There are two major examples or instances of it. One is ISIS, or intermediate system to intermediate system. The other one is OSPF. OSPF is what is used to do routing on the Berkeley campus. And it works really differently than distance vector. So let's kind of explore link state and kind of sketch out the design for it. So we're going to try to position it against a distance vector. So distance vector is doing this global computation, right? It's distributed. It's asynchronous, right? It's this distributed computation that uses local data, right? The data that it's acting on at any particular time is just the data that it got from its neighbors, right? Link state is like the opposite. It's doing a local computation using global data from far away in the network. And so what does that mean? Well, hopefully the distance vector part makes sense to you, at least a little bit, what I'm getting at there, right? This distributed computation shares data with its neighbors, right, with these advertisements. So let's look at the link state part. So a router locally computes routing state using global data from all parts of the network is what I wrote on that last slide. So what is this global data that I'm talking about? It's the state of every link in the network. So every router is locally computing using information about the state of every link in the network. Is that link up? What is the cost of that link? So if someone told you that there was a link R1, R2 with a cost of 1, right? It's the state of that link. It exists, it's got a cost of 1. Then you know there's two routers, R1 and R2, and you know there's a link between them with a cost of 1, right? If they tell you there's a link R1, R3, which exists and has a cost of 10, then you can kind of add that to your mental picture of what this network looks like, right? And so on and so on. R4 to R5 exists and has a cost of 7. So, okay, there's two routers, R5 and R4, with a link of cost 7 between them. R1, R4 has a cost of 2. So you can fill that in. R2, R5 has a cost of 1. R3, R4 has a cost of 1. And, so on and so on. And so you could sort of build up this map of the topology. What's missing from this? Or, to jog your thinking, like, what, we have some of one thing and none of another thing in this topology that we've drawn. What's missing? Yeah?
We don't have any hosts.
We don't have any hosts, right? So we also want some host information, right? Like destinations more generally, right? So information about destinations. R3 has destination A. R4 has destination B, right? Those statements, we can add those to our picture, right? And now we have this complete map of what this topology looks like, just by listening to information about individual links and about where the destinations are. Does that make sense? Thumbs up? Makes sense? Thumbs down? Not so much? All right. So if the router has a global view, you can pretty easily compute paths, right? Like, imagine you're R5. What's the best path to A? Well, it's R5, R2, R1, R4, R3 to A. Right? So that's not too hard to figure out on this particular topology. And so what of that information is actually useful to R5? Yeah?
Forwarding to R2.
Forwarding to R2, right? That's the only piece of that path that's actually useful to R5, right? Like, R5 has this table, right? The only thing in it is the next hop, right? So what's the next hop from R5? It's R2, right? So it computes the path, and only that next hop is actually useful to it. And so every router can do basically this same thing, right? And so, the routers in these protocols basically follow these 4 steps. They need to get the state of all the links and the location of all the destinations, right? That's what we said, just calling out, these links and the costs and the destinations. And we're going to use that global information to build a full graph, like I just said. We're going to find paths, from ourself, from whatever router we are, to every destination on the graph. And we're going to use the second hop in all those paths to actually populate our forwarding table, right? These are the steps that link state's going to use. These all kind of make sense? We don't know how to do them yet, but does this make sense why this would work? Thumbs up if it makes sense. Thumbs down, you're not so sure? A lot of people not willing to commit. That's all right. All right, so let's walk through them. So, we need to get all this global information that we talked about, right, about the state of links. I'm not going to talk about that just yet. We're going to come back to it. We're going to use that global information to build the graph. And we just saw how to do that a second ago, right? We sort of just paste together all these individual messages about neighbors and destinations, right? We just sort of paste them in together, and we get this, graph of the entire network, right? We're going to find paths from ourselves to every destination on the graph. And, since the router has the complete topology, it can basically do this however it wants, right? For least cost paths, this is called the single source shortest path problem. And so, note that this isn't a distributed asynchronous algorithm like with distance vector. Like, each router is really just running, whatever algorithm it wants to find paths starting from itself. So, we know a couple for this already, right? I mean, you could use Bellman-Ford, not the distributed version. You could just use the plain old textbook Bellman-Ford algorithm, right? Just the router runs it, figures out what it thinks the paths are, installs the next hop for each destination, right? You could use Dijkstra's, as someone pointed out. That's more efficient, in a lot of cases anyway, if you look at the complexity. Can you do better than these? Anybody want to volunteer a way you could beat Dijkstra's? What if your graph isn't weighted? Is Dijkstra's the most efficient? Breadth first search. Dijkstra's is basically just like a fancy breadth first search. But if you don't need weights, breadth first search will smoke it. You can do other things. There's a class of algorithms called dynamic shortest path algorithms. And the idea there is that often you've got some graph, right? And you can compute shortest paths on it. And then maybe you add an edge or you remove an edge, right? Like a link fails or something, right? But the graph is still mostly the same. So, I mean, you could run Dijkstra's again from scratch. But these dynamic shortest path algorithms take advantage of the fact that the graph is mostly the same as the last time you did it, and that you usually only mutate it a little bit, right? You add a link here, you add a node here, etc. So there are these dynamic algorithms which can be quite a bit faster. There are approximate shortest path algorithms, right, which often have much better runtimes. There's also parallel shortest path algorithms, which might have better runtimes. And so there's probably some others that I'm forgetting too. So, there's this whole array of things you can do to do this quickly, which is important if you have lots and lots of routes. But the thing to note here is that, there's nothing that says you even need to do least cost routing. Right? You're just doing this centralized computation. You can pick the paths however you want, with a caveat that I'll come to in just a second. So the last thing is you use the second hop in those paths to populate the forwarding table, right? And so it's important to remember that each router only influences its own next hop behavior, right? Other routers must be coming up with paths that are compatible to the ones that you come up with, right? If you're doing least cost routing, this is really easy if you're minimizing the same cost and if all the costs are greater than 0. And of course you have to agree on what the topology looks like. But given those two, you don't even need to implement exactly the same algorithm. You don't need to break ties the same way, for example, because if every time you forward it, it's getting closer to the destination, then the next hop is never going to send it back to you, right? You're never going to get a loop. So a counterexample here is R2 and R5 both compute apparently feasible paths, right? Both of these, R2 thinks the path is going to go R2, R5, R4, R3, right? R5 thinks it's going to go R5, R2, R4, right? Both of these, would work if that was the path that packets actually took. But they don't work together, right? So, R2 is going to forward it to R5. R5 is just going to forward it back to R2, which is just going to forward it back to R5, right? Does that make sense? The paths that you choose have to be consistent across routers. Yeah? All right. So it populates your tables and you're done. Except for the tricky part, which is the part that I skipped earlier. So you need to get the state of all the links and the location of all the destinations in the network, right? You need to build that map, right? That's going to be the tricky part. So all the routers need information about all the links between all the routers, right? And they need to know where all the destinations are attached to the routers. So we can sort of break up what needs to happen here into 3 steps. And so every router must find out who its neighbors are, first of all. Right? That's the first step. You find out who your neighbors are. Then you tell everybody in the entire network who your neighbors are. That is, about your links between you and your neighbors. And then you tell everybody about the adjacent destinations, right? What destinations are attached to me. And so starting with the first one, how does a router find out who its neighbors are? How does anybody find out who their neighbors are? You introduce yourself, right? So, you say, hi, I'm Charles. Hi, I'm Ada. Hi, I'm Margaret, right? And after everyone says hello here, Charles learns, okay, my neighbor said she was Ada, so I know I have a neighbor named Ada. And you can look at that as a graph, where it's like, okay, here I am, I'm Charles, and I've got some neighbor Ada. And Ada learns from her neighbors, okay, I've got a neighbor Charles and a neighbor Margaret. And so I can put them in a little graph, right? Margaret learns that she's next to Ada. And so basically, routers periodically send hello messages to their neighbors. They just say, hi. And if a neighbor goes quiet for a certain amount of time, very much like with distance vector, we have these timeouts, this expiration. So if a neighbor goes quiet, you eventually assume that that neighbor is gone. Does this make sense, how this works, how this lets you discover your neighbors? So you know who your routers are, your immediate neighbors are, by exchanging hello messages. So now you need to tell everyone about your neighbors so that everybody knows who's connected to who. And so in order to do that, we use a process called flooding. And so the idea is, when you have interesting local information, you send it to your neighbors. And here are our three friends again. And maybe Margaret has just learned that she's friends with Ada. And so she tells her neighbors, Margaret is neighbors with Ada. And her neighbors hear that. And her neighbors pass that on to their neighbors. And so now everybody knows that Margaret is neighbors with Ada, right? Like Ada might have already known that because she's also neighbors with Margaret, but Charles wouldn't have known that, right? He's not a neighbor to this conversation. So by sort of passing it between us, we've all learned it. Does that make sense? It's sort of like gossiping about your neighbors. So does that always work? Anybody think this always works? Thinks there are cases where this doesn't work? If I tell my neighbors, and those neighbors tell their neighbors, and those neighbors tell their neighbors, and those neighbors tell their neighbors, is this going to work? Is everybody going to learn? Yeah.
So when the network gets super duper big, everything is going to work.
When it gets super
Super big.
super big.
If the network delay is not catch up with.
Yeah, so maybe this doesn't scale very well. You're right. Maybe when the network gets super big, maybe this doesn't work. So maybe there's a scaling problem. We're going to assume for now that the network is a manageable size, though. But good idea. Yeah. Maybe the graph's not connected, right? So that's certainly true. You know, you may pass it on to all your neighbors, but not everybody learns because the graph isn't connected. And that's true. On the other hand, it kind of doesn't matter. It actually works out well, right? Because, like, there's no point in people who in a disconnected part knowing anything about your part because they couldn't possibly reach you anyway. But you're right. Yeah? If you drop a packet, sure. Yeah, let's come back to that one. But then let's assume for now that they go through. But yes, good. Yeah?
What if your state changes while you propagate different state, and like one router will receive two different states?
Yeah. So it's possible that, you get one and then you get another, like maybe Margaret says, maybe you get a message that says, Margaret is neighbors with Ada. And then you get one that says, Margaret is neighbors with Frida. And you're like, which of these is true? So yes, that's another one. Do you
Could the neighbor dies while you're still trying to pass the message?
Yeah, a neighbor could die. So these are all some interesting thoughts, but there's a really fundamental, really big problem. I mean, you're all getting some corner cases. Like we're going to probably deal with a lot of these as we go on. But there's a really fundamental problem going on here. And so I will show you why, though it's difficult considering I can't really see the screen over here. All right, so here's a graph, and R1 might send a packet on this topology. And you can see it tells everybody. R5 tells both of its neighbors, and it gets to everybody. Same with R2, it gets to everybody. Same with R3. If R3 sends a packet, and everybody just tells their neighbors, it gets to everybody. So this seems to work. In fact, any node on here will work just fine on this topology. But what happens when we add a loop to this topology? R1 sends it, it gets duplicated there, and now what's going on? It's just kind of sending around and around this cycle forever in opposite directions. And this will just go on forever and ever. So that's not great. Things get so much worse. What if we add a second loop? Now what's going to happen? R1 sends a packet, gets duplicated by that first loop. Both of those duplicates get duplicated by the second loop, which all get duplicated by the first loop again, which all feed back into the second loop. So this is exponential growth in the number of duplicates of this packet. On a real network, this will consume all of your bandwidth immediately. So, bad news. The naive solution, just telling all your neighbors, doesn't work when the topology has loops. With one loop, packets loop around the cycle forever. That's bad. When you have multiple loops, packets multiply exponentially, which is very bad. So what's the solution? There are a number, but we're going to start with a pretty simple one here. So this is the statement we had before. When you have local information that's interesting, send it to all your neighbors. Right? Something happens to me, I tell everybody. And when you receive this information from a neighbor, you send it to all your other neighbors, right? That's the basic flooding algorithm, the naive one. How do we fix it with one statement? Anybody have a good idea for how we can fix this? Yeah. Yeah, when you receive new information, right? So I'm going to phrase it as, unless you've already seen this info packet, in which case drop it. So you flood it to your neighbors unless you've already seen it. So how do you know if you've already seen it or not? The easy solution is that routers keep a sequence number, put a sequence number in each of their updates to their neighbors. So the idea is every router has its own sequence number, and when it sends a routing message, it puts that sequence number in the packet and increments it. Right? So every update it sends has an increasingly large number, right? So every router also tracks the largest sequence number it's seen from every other router. And so if it sees an update with a smaller or equal sequence number, then the update's old. It's already seen it, right? If it sees an update with a larger sequence number, then that update is new. It's never seen it before. So it remembers the highest sequence number associated with the router that sent that update, and then it floods it to its neighbors. Yeah? Is there a point when this number resets? With a finite number of bits, it has to, right? So yes, there is a point. We're going to ignore it for the sake of this class. The algorithms to deal with that correctly can actually be a little bit subtle. But also, if you've got like a 64-bit number, for example, it might take a pretty long time. Yeah, so it might make sense to build resetting into this. Yeah. So there are some tricky things that have to do with eventually it's going to have to wrap around or whatever. We're going to ignore them and assume that you can just keep counting up. Does this make sense as the basic idea, how this works and how this prevents you from looping infinitely? Thumbs up if you kind of got it? Yeah. All right. So, quick question here. Would this be a problem if we use this protocol as an EGP, as an internet scale routing protocol? Sure it would, right? You don't want to remember the sequence number for every single router on the internet. All right. So this question kind of came up earlier. How do you make flooding reliable, right? Packets could drop while you're doing this flooding process, right? So who's got a quick idea of how you could make this kind of reliable? What's our favorite trick for making things reliable? Yeah. Periodically re-advertise it, right? Yeah. So you can just periodically resend things. right? ISIS and OSPF both do this. They also do some more clever stuff, which basically lets them get higher reliability with fewer retransmissions. We're not going to explore this idea of good reliability algorithms in the context of link state or of routing. We're going to talk about reliability kind of a little bit more generally in week 6. But baseline, you can just repeat yourself, right? That'll work. So, the second thing, we need to tell everybody about our neighbors, and we're going to do that by flooding this information, right? The final thing was we need to tell everybody else about any adjacent destinations, right? Like about what hosts kind of are nearby. And we do that by just flooding that information too, right? We've got this mechanism now for flooding information to everybody, so we use that same mechanism. So, basically you've got something like this, and maybe R3 has a static route to A, right? So it's like, hey everybody, I can reach A with a cost of 2. So it floods that to its neighbors, and they're like, yeah, all right. And they flood it to their neighbors, and now everybody knows. So, tell everybody about adjacent destinations by flooding info about those destinations. That was the third step. So by implementing all of these, routers work together to share their local information globally. Does that make sense? So if you remember, going way back now, all of this was in service of, the first part of the protocol where we said that we needed to share links and destinations. And now we know how to do that by sending hellos to learn about our neighbors and by flooding the information that we learn. And so we're done. That's link state, right? So any questions? Yeah?
I'm getting nervous when you say flooding because I think it could be exploited. Could you see a point to that?
Yeah, so you're worried about flooding because you think it could be exploited. And yes, it can probably be exploited. It's probably not the only exploitable thing or the most exploitable thing. We're going to put security aside in this and just assume that this is going to work okay. The internet has gotten by with for a long time without worrying about this too much. And remember, we're generally talking about interior gateway protocols here, right? So this is, again, it's the routing that happens inside a network that you own. So it's not like you're necessarily vulnerable to people far away. But you're right. Certainly, there are vulnerabilities to this sort of thing. So a couple statements here on link state convergence. We're using the plain non-parallel Dijkstra's algorithm, right? Or whatever pathfinding algorithm we want. And Dijkstra's algorithm is never going to find a path with a loop. So therefore, with link state protocols, we're never going to have loops. Is that true or false? Anybody want to say why they think what they think? Anybody want to? Why is it true or not true that we will get loops with link state protocols? Yeah.
It could be false because the paths that the routers individually determine to end on.
Yeah, it could be false because the paths that the routers individually come up with aren't compatible with each other, right? Since they're only responsible for their next hop. And so it's definitely false because we only have control of our next hop. And in particular, if routers don't have the same view of the global topology, right, then all bets are off, right? For example, in this case, R1 doesn't know about the failure yet, right? Because it's far away. R3 knows about it because it's right there. But R1 hasn't gotten an update yet. So, if R1 gets a packet to A, it's going to send it to R3. R3 is going to say, oh, well, I've already figured out a good new path. It goes R3, R1, R2. Right? So it's going to send it back to R1. R1 still hasn't gotten the update. It still thinks the best path is through R3, right? So you can definitely still get a loop here. So what are some sources of convergence delay with link state algorithms? Well, you've got the time to detect a failure, right? You can't respond to the failure until you know the failure is there. You've got the time to flood the link state information, right? Which is going to be proportional to how the diameter of the network, right? How far away another node can be. And then there's the time to recompute the paths and update the tables, right? So during that period of time, right, between like a failure and when you've, done those three things, you can have dead ends, you can have packets looping, you can have out-of-order packets reaching the destination, right? So like you sent packet 1 and then packet 2, but the destination gets packet 2 and then packet 1, right? Usually that doesn't cause semantic problems, but it can cause performance problems for reasons you will find out about when we get to talking about TCP. And so the timeline for local failures. First, when a failure first happens, you've got this period of time where the failure hasn't been detected yet, right? And so the packets are sent into a dead link. Those packets are lost, right? Eventually, the adjacent router, the one next to the failure, realizes there's a failure, but it hasn't computed, new routes or new table entries yet, right? So that's like a dead end, right? It's going to get the packet, and it's going to be like, well, I know the link I had is dead, but I haven't figured out what else to do about it, right? Eventually, that adjacent router, the one right next to the failure, is going to compute some new path, but nobody else knows anything about this yet, right? And so during that period of time, you could have loops, right? Because when a packet gets to that one where the failure was, that router is going to say, oh, well, I'm going to send it on this other path. Maybe that's back the way it came, maybe it's somewhere else, but there's a possibility that whatever chain of neighbors I send it to is just going to come right back through me, right? So you might have a loop transiently here. As different nodes become aware, different routers actually get the new link state messages that tell them that this link is down, right? Routes are going to start changing over the network. So you might have some loops at this point. You also potentially have reorderings of packets again, like where packets I mentioned, they come in a different order. So why is that? Why do you potentially get packets coming out of order during this period of reconvergence? Anybody have a sense of why that is? Well, a simple example we can go through. Where did it go? I've lost it. There we go. All right. So you can think about an example here, right? So maybe there's a packet to A at R3 at the same time that a packet to A arrives at R1. And this is at the same time that R1 learns that the link had gone down, right? All these things happening at once. So R1 now knows the better path, right? So the second packet, right, at R1 is going to take the path on the left side here. Meanwhile, the one at R3, if it was going to make it there, it's going to have to back up and go back around from R3 to R1 and then to R2, right? So the packet that had gotten further now has to backtrack to get there, right? So the one that didn't have to backtrack is going to beat it there. Does that make sense? So these packets can come in different orders. More generally, just you're going to end up, when you're adapting to failures, things are going to take different routes, and some may be faster than others. All right, any questions on link state routing? Yeah. What's the benefit over distance vector? Yeah, so I think you can come up with a number. A number for one, on different topologies. They are going to have different convergence properties, right? Again, it's going to be sort of dependent on the topology. Potentially, link state was originally developed because of sort of like stability problems with distance vector, due to the fact that it has to count up sometimes and things like that, which I think especially when it was used for like more of the network, like for the internet at large, were problems. Also before some of the enhancements that were made to distance vector were problems. But there are some others, like for example, if you want want to compute your paths using some really weird pathfinding algorithm, it's pretty easy to do that with link state, right? With distance vector, it's just Bellman-Ford. Your options are minimize some cost metric, and that's it, right? So it's also a little bit more flexible. So flexible, some people would say it's kind of can be more stable, can be faster to converge, which I certainly buy for old versions of distance vector. For modern versions, I'm less sure, but that's an argument anyway. All right, so link state in a single slide. It's super simple conceptually. Everyone floods link and destination information. Everyone then has a global map of the network. Everyone independently computes the next hops. All of the complexity is in the details of doing these things. All right, so now in the remaining few, gonna start to talk about learning switches and spanning tree protocol. We will not get through it, but we'll start. So we've been looking at distance vector and link state, where the tables are filled by this sort of like ongoing independent routing process, right? And all of these routes have sort of been seeded with these static routes for destinations. And these two, classes of routing protocol are really common for routing at the network layer, like L3 with IP addresses, right? So let's look at a really different way of doing things, which is with learning switches. And so with learning switches, the tables are filled in opportunistically using the data packets instead of this sort of like ongoing routing process. And there's no seeding with static entries required. And this is super common for routing at layer 2, in Ethernet in specific. Many people would say that this isn't actually properly routing, but it solves the same problem of filling in tables. So I'm going to call it routing. So the idea here is that when a data packet arrives at a switch from some neighbor, like here, there's a packet from A to B arriving at S1. S1 knows that it can reach the source of the packet using that neighbor, right? Like if you follow the packet backwards, you're going to reach who sent it, right? Does that make sense? So we use the source address in the packet to create a table entry for packets destined to that address, right? This packet came from A, so that we know we can use A by sending the packet backwards. So this packet is going to B, and we don't have a table entry for B. So what would we have done so far with everything we've talked about at this point? What happens when a packet arrives at a router that doesn't know anything about that destination? You drop it. In this case, we're going to do something else. We're going to be optimistic. We're going to assume that B is out there somewhere. So we flood it to all our neighbors, right? And so S2 and S4 now get this packet, and they both learn that they can reach A using S1, right? It got a packet from A, from S1, so therefore A must be in the direction of S1, right? They also don't have entries for B, so they also flood it. S3 learns that it can reach A through S2. S5 learns that it can reach A through S4. They don't have entries for B, so they flood it, and look, B got the packet. So, because we kept flooding it, if there was any way for it to get there, it's going to get there, right? So usually communication isn't unidirectional, right? Usually if I'm talking to you, you're talking to me. So what if B replies to A? So now we have a packet from B to A. It arrives at S3. Well, when it gets to S3, there's our table entry for A, right? This packet can just follow a path straight back to A. It doesn't need to flood it anywhere. It's just following the table entries. Moreover, as it goes, it's leaving behind table entries pointing to B. So now, if A sends another packet to B, this doesn't need to flood either, right? We've now got table entries in both directions between A and B. We've fully populated this path between A and B. So what's the big problem here? Where does this break down? Yeah? If you're flooding every packet, So if you're flooding every packet, maybe it's a lot of like extra traffic, right? Sure, maybe it's not the most efficient use of your bandwidth. Even worse than that, give you a hint, we saw an example earlier. Yeah. What if you have a loop, right? Like, that's bad news. We already saw that. So this doesn't work when there's a loop. So the major problem with order switches is that floods, when the destination is unknown, and floods have problems when the topology has loops. And our previous solution to this problem doesn't work in this case. And I will come back to it in a second, by which I mean Thursday. I think I will, I'll make one last statement, one last note, which is, the decision to flood or not is done on this like switch by switch basis, right? Like packets are not purely flooded or purely sent just between neighbors for like the entire lifetime of that packet, right? Instead, at each switch, packets are either sent out the correct port if you have a table entry for it, or they're flooded, sent out all the ports except the incoming port if they're not. The whole algorithm looks something like this. We've got 40 seconds. The quick part of it is, when a packet arrives at some switch, the first thing you do is learn from that table entry. You set the table, you use the source address, you set the next hop to the previous hop, where the packet came from. And then you set some TTL, so eventually this table entry times out. Then you forward it. If it's in the table, you send it to the next hop, unless the next hop is the hop that the packet came from, right? If you're going to try to send it back, the packet back the way it came, if you're going to try to forward it directly back, don't bother doing that. The switch that it gets to is probably just going to send it back to you again. You've got this really tight loop. Otherwise, you do send it to the next hop. And if you don't have it in the table, you flood it to everybody. And so that's the basic algorithm. We will pick this up on Thursday. Thank you so much.
You're welcome. Yeah. So basically,